The straight line path of a particle is defined using a coordinate axis such as the s-axis shown below. The position coordinate s, this coordinate here, measured from a fixed origin O, is used to specify the location or position of the particle at any given time. The magnitude of s is the distance from O to the particle, typically measured in meters or feet. Based on the defined positive s direction as to the right, the sign of s is positive if the particle is located to the right of O and negative otherwise. Realize that position is a vector quantity since it has both magnitude and direction. But here it's being represented only by the scalar s, since the direction always remains along the coordinate axis. And of course, s can be positive or negative, but it never comes off of this coordinate axis. So in this case, this particle here has a positive value of position because it is currently located to the right of point O in the direction of positive s. As a particle moves, it experiences a change in position and thus a displacement. If s represents the initial position of the particle and s prime represents its final position, then displacement delta s is defined as follows. Delta s equals s prime minus s. That's final position s prime minus initial position s. In the scenario illustrated below, displacement is positive since the particle's final position is to the right of its initial position, and therefore s prime is greater than s, so delta s would therefore be positive. Keep in mind that displacement is a vector quantity and is distinctly different from distance traveled. So whereas displacement is a vector quantity with both magnitude and direction, distance traveled is a scalar quantity with no specific direction. Distance traveled is defined as the non-negative scalar that represents the total length of the path over which the particle travels during a segment of time. The magnitude of the displacement of a particle during a specified time period is not necessarily equal to the distance traveled. For instance, if a particle changes direction during its motion such that it begins moving away from the origin, then returns to the origin, its total displacement is zero because it started and ended at the origin. But its distance traveled is a non-zero positive quantity because it did traverse some amount of distance, some length, some distance traveled. Let's now discuss velocity, the time rate of change of the particle's position. During a finite period of time, meaning a non-zero but non-infinitesimal period of time, we can calculate the particle's average velocity, v sub average, as displacement divided by elapsed time, where v sub average equals delta s over delta t, represented mathematically. At a single instant in time, we can determine the particle's instantaneous velocity v as the first time derivative of position. That is, instantaneous velocity v equals ds by dt. As a vector quantity, velocity has both magnitude and direction. And here in this diagram, we're representing that velocity vector as this arrow here to the right, as it moves to the right. Typical units of velocity are meter per second and foot per second, since we have a displacement over an amount of time. Let's now distinguish speed and velocity, much like we did displacement and distance. So whereas velocity is a vector quantity with both magnitude and direction, speed is a scalar quantity with no specific direction. Speed is defined as the non-negative scalar that represents the magnitude of the particle's instantaneous velocity. Average speed of a particle during a finite period of time is defined as the total distance traveled during that time divided by the elapsed time. So we denote that as v sub average sub sp for speed. That equals s sub t over delta t. This s sub t represents total distance traveled, during some amount of time. So this is how to calculate average speed. Again, it's never negative, only positive or zero. Moving on from velocity, we now have acceleration, time rate of change of a particle's velocity. During a finite period of time, we can calculate the particle's average acceleration, a sub average, as the change in its instantaneous velocity, delta v equals v prime minus v. So a sub average is therefore delta v over delta t. At a single instant in time, we can determine the particle's instantaneous acceleration a as the first time derivative of velocity, or equivalently, the second time derivative of position, where mathematically a equals dv by dt, which equals d squared s by dt squared. As a vector quantity, acceleration, like velocity and position and displacement, has both magnitude and direction because it is a vector. Typical units of acceleration are meter per second squared and foot per second squared. Also on the topic of acceleration, if a particle is slowing down, in other words, its speed is decreasing, the particle can be said to be decelerating. In this case, the acceleration vector shown here acts in the opposite direction to the velocity vector. Keep in mind that even if a particle is momentarily at rest, it may still have a non-zero instantaneous acceleration if a moment later it has a non-zero velocity. For instance, as an object is thrown upward, let's say you're on the surface of the Earth and you're throwing a ball upward, the ball momentarily stops moving when it reaches its highest point. Then, after that moment of stopping its motion, it then begins moving downward. Although its velocity is zero at its highest point because it is momentarily at rest, its acceleration, however, is not zero, as the object is constantly subjected to downward gravitational acceleration. Another important differential relation that can be derived from those two kinematic equations is shown here from those two previous equations, which are v equals ds by dt and a equals dv by dt, is this one here, a ds equals v dv. Notice that there's no variable here that involves time. Okay, this equation can be useful in some problems. In the special case that a particle experiences constant acceleration a sub c during its motion, each of the three kinematic equations previously mentioned, the time derivative equations, can be integrated to obtain the following useful formulas. Here are those three equations. V equals v naught plus a sub c t, s equals s naught plus v naught t plus 1/2 a sub c t squared, and v squared equals v naught squared plus 2 a sub c s minus s naught. Now remember that subscript of 0 we refer to as the naught subscript, meaning t equals 0. And also t here is some elapsed time period, so we could also call it delta t instead of t. It is some period of time.